chemical reactions. Aldehydes and ketones are reduced to the corresponding alcohols by A. Addition of hydrogen in the presence of catalysts like finely divided platinum, palladium, nickel, and ruthenium. RCHO plus H2 in the presence of PD give RCH2OH. This method is called catalytic hydrogenation. B. Treatment with chemical reagents such as sodium borohydride NaBH4 or lithium aluminium hydride LiAlH4, CH3CHO ethanol plus 2H in the presence of H2Ni or LiAlH4 give CH3CH2OH ethanol. Aldehydes yield primary alcohols while ketones give secondary alcohols. Nucleophilic addition reactions. Being unsaturated, aldehydes and ketones undergo addition reactions. They have a polar carbonyl group. The carbon of the carbonyl group, being electrophilic, is readily attacked by the nucleophiles. Some important examples of nucleophilic addition reactions. A. Addition of hydrogen cyanide, HCN. HCN adds to aldehydes and ketones to form cyanohydrins. Cyanohydrins are useful synthetic intermediates. B. Addition of sodium bisulfite, NaHSO3. NaHSO3 adds to aldehydes and ketones to form crystalline addition products. C. Addition of Grignard reagents. Aldehydes and ketones add on to Grignard's reagents to form alcohols on hydrolysis. Examples of organometallic addition reactions. Grignard's reagents gives a primary alcohol with HCHO, a secondary alcohol is produced with any other aldehyde, and a tertiary alcohol with a ketone. D. Addition of alcohols. Aldehydes react with alcohols in the presence of dry HCl gas to form a gem dialkoxy compound known as acetyls. Intermediate compound hemiacetyl is an unstable compound and cannot be isolated. It further reacts with alcohol to form stable acetyl. Ketones react with ethylene glycol to form cyclic products known as ethylene glycol kettles. Formaldehyde reacts with ammonia to form hexamethylene tetramine CH2-6N4, also known as urotropine. Urotropine is used as a medicine to treat urinary infections. Nitration of urotropine under controlled condition gives an explosive RDX, research and development explosive. Reduction to hydrocarbons. The carbonyl group of aldehydes and ketones is reduced to CH2 group on treatment with zinc amalgam and concentrated hydrochloric acid. Clemmensen reduction. Wolff-Kishner reduction. Aldehyde ketone is treated with hydrazine followed by heating with potassium hydroxide in high boiling solvent ethylene glycol. Benzaldehyde is reduced to toluene. C6H5CHO benzaldehyde in the presence of NH2NH2 KOH 455 to 475 K ethylene glycol gives C6H5CH3 toluene plus H2O plus N2. Hydroiodic acid and phosphorus reduce carbonyl compounds at 425 K. Acetaldehyde is reduced to ethane. CH3CHO acetaldehyde plus 4HI in the presence of P at 425 K give CH3 single bond CH3 plus H2O plus 2I2. Oxidation reactions. Aldehydes are readily oxidized to carboxylic acids on treatment with common oxidizing agents like nitric acid, potassium permanganate, potassium dichromate, etc. Even weak oxidizing agents like bromine water, Ag+, Cu2+, etc. are effective. As a result, aldehydes act as strong reducing agent. Ketones are not easily oxidized. Under vigorous condition, they are oxidized to carboxylic acids having lesser number of carbon atoms than the parent ketone CH3C double bond OCH3, which appears as a yellow precipitate in the presence of O concentrated HNO3, gives HCOOH formic acid plus CH3COOH acetic acid. These oxidation reactions can be used to distinguish aldehydes from ketones. Tolerance test. On warming an aldehyde with freshly prepared ammoniacal silver nitrate solutions, tolerance reagent, in a clean test tube in a water bath, a bright silver mirror is produced due to deposition of silver metal on the sides of the test tube. CH3CHO liquid plus 2 Ag NH3 whole 2 plus aqueous plus OH minus aqueous CH3COO minus aqueous plus 2 Ag plus 2H2O plus 4 NH3. Ketones do not respond to this test. Aldehydes respond to the Felling's test. Felling's solution is an alkaline solution of copper sulfate containing sodium-potassium tartrate, Rochelle salt as a complexing agent. Aldehydes, on warming with solution, give a red precipitate of cuprous oxide as a result of the redox reaction. Aromatic aldehydes give very poor results in this test. Halo form reaction. Ketones having at least one methyl group linked to the carbonyl carbon atom, that is, methyl ketones, are oxidized by sodium hypohalite to sodium salts of carboxylic acids with one carbon atom less than that of the ketones. The methyl group is converted to halo form, which appears as a yellow precipitate. Aldol condensation. Aldehydes and ketones undergo a reaction in the presence of dilute alkali as catalyst to form beta-hydroxyaldehydes, aldol, or beta-hydroxyketones, ketol, respectively. This is known as Aldol reaction. The aldol and ketol readily lose water to give alpha, beta unsaturated carbonyl compounds, which are aldol condensation products, and the reaction is called aldol condensation. Cannizzaro reaction. Formaldehyde, which does not have an alpha hydrogen atom, undergoes self-oxidation and reduction, disproportionation reaction, on treatment with concentrated alkali. In this reaction, one molecule of the formaldehyde is reduced to alcohol, while another is oxidized to carboxylic acid salt. Electrophilic substitution reaction. Aldehydes and ketones undergo electrophilic substitution at the ring in which the carbonyl group acts as a deactivating and meta-directing group. Nitration of benzaldehyde with concentrated HNO3, H2SO4 at 273 to 293 K gives meta-nitrobenzaldehyde.